Hello everyone. Lesson number 14 is about simple circuits where the focus will be on continuous electricity that involve electric current. In order to build a simple circuit, you need three components. The first component is charge separation, where the positive and negative can be separated and potential difference can be produced. The second component is conductor that will furnish the path for the charges to move. And the third component is the active device that we need to operate using electricity. Now with regard to charge separation, there are three methods to separate charges. One of them, the primitive one, is rubbing materials, which we addressed in the previous lesson, lesson number 13, which has to do mainly with static electricity and hence is not very practical. The second method is batteries, and we addressed batteries in lesson number 13, where it's made of two metal electrodes that have different oxidation reduction values, and they are inserted into the appropriate electrolyte that cause one of the electrodes to lose electrons, and that's oxidation, while the other electrodes will gain those electrons, and that's the process of reduction. And the electrolyte, which is mostly an acid, will provide the electric charges, therefore the electric current will be continuous. The third method is generators, and the key concept behind generators is the change in the magnetic field induced electricity, and we'll talk about generators in more details in lesson number 16. Now regarding to the conductors, as we know, metals in general are good conductors of electricity, and the reason is they have free valence electrons. Electrons in the outer level are free to move in the case of metals because they are loosely bounded to the nucleus and hence can provide charges that will make up the electric current. So now let's use the electric terms here to describe each one of those previous statements. The method by which the charges are separated, we call it the voltage source. And voltage is defined as the amount of work done per charge. Hence, the higher the voltage, the more work done per charge. And we know the charges are electrons because protons are confined within the nucleus. So in terms of equations, voltage, which we give it a symbol V, is equal to the work done, so it's work over charge, the work done per charge. This is the voltage, and the unit of voltage is volt, where 1 volt is equal to the unit of work per unit of charge, so it will be 1 joule per coulomb. That's 1 volt, it's 1 joule per 1 coulomb. So if you have 1.5 volt battery, this means this battery has the ability to perform 1.5 joules of work per 1 coulomb of charge. Now recall that 1 coulomb of charge is equal to 6.25 times 10 to the power 18 electrons. We calculated this number last time in question number 6 in the discussion. So basically 1 volt will be 1 joule of work done per 6.25 times 10 to the power 18 electrons. 13 volt battery, like your car battery, which is between 12 to 13 volts, has the ability to perform around 12 joules of work per 1 coulomb, meaning per 6.25 times 10 to the power 18 electrons. And this work will be able to push those electrons to move continuously, creating continuous electricity, which is electric current. And the other component of the electric circuit, other than the voltage source, is the active device, which is the purpose of the electric circuit. We use electricity to operate electric devices such as electric motors, electric lights, and so on. And each active device has certain resistance. This resistance will dissipate energy and use certain power output, and we'll address that as part of Ohm's law. Now the third component is the current flow, which will be actually flowing through the electric wires, the conductors, and the best conductors are silver and copper. Electric current are charges that are in motion. They cannot be static, they have to be in motion. And hence electric current is defined as the charge per time, meaning the amount of charge that pass through any point in the circuit per second. The symbol for the electric current is I, and it's the rate at which the electric charges are moving per time. So it's basically equal to the amount of charge Q divided by the time T. If the time is big, meaning the charges are still, the electric current will be close to zero. And if the time is short, meaning the charges are moving fast, then the electric current will be big. The time and the electric current are inversely proportional. Now what's the relationship between voltage and current? As you mentioned, the voltage is the work done per charge, so the more work done, the more charges are pushed by that work. And the more charges are pushed, the bigger the electric current. So voltage and current are directly proportional. This symbol here means directly proportional. And this is when the resistance is constant. Now how about the relationship between resistance and current? Now resistance is resisting the current. So the bigger the resistance, the smaller the current. Hence current and resistance are inversely proportional. The symbol here followed by the inverse of the quantity means inversely proportional. And this is of course when the voltage is kept constant. So from this relationship we can see that the current can be written as voltage over resistance because the current is directly proportional to the voltage and inversely proportional to the resistance. The unit of electric current is amps, or A for short. And 1 amp will be equal to the unit of charge divided by unit of time. So 1 amp will be equal to coulomb per second. So basically if you have 1 amp of electric current passing through the circuit, this means you have 1 coulomb of charges going through any point in the circuit per second. And as we know, 1 coulomb represents 6.25 times 10 to the power 18 electrons. So 1 amp of electric current means 6.25 times 10 to the power 18 electrons passing any point in the circuit per second. Now let's look at this relationship between electric current and voltage and electric current and resistance, which constitute what we call it Ohm's law. Now let's say we have this electric circuit where the voltage is 1.5 volts and is connected through those wires to the resistance. So this cylinder here represents the resistance and the circuit is complete. Start from the positive of the battery across the resistor, then back to the negative terminal of the battery. Now we are going to explore the relationship between voltage and current when the resistance is set constant. So here we'll set the resistance at 500 ohms. And by the way, this symbol here is the unit of resistance. Uppercase omega stands for ohms, OHMS, and we'll keep the resistance constant while we'll vary the voltage and monitor the impact on the electric current. Now here when the voltage is 1.5 volts, the current is 3 milliamps. Now what will happen here if we double the voltage from 1.5 to 3 volts? What do you think will happen to the current? Will it increase, decrease, stay the same? And if it increases or decreases, by how much? So let's double the voltage from 1.5 to 3 and notice here what's going on with the electric current. As you see here, when we double the voltage from 1.5 to 3 volts, the current has doubled. It went from 3 milliamps to 6 milliamps. What happens if we triple the voltage from 1.5 to 4.5 volts? So now notice the current here is increasing as well. And now we have 4.5 volts total. And the current is 9 milliamps. So the current tripled from 3 milliamps when the voltage was 1.5 volts to 9 milliamps when the voltage is set at 4.5 volts. So we can see here that the voltage and the current are directly proportional, meaning if you increase the voltage by a factor, the current will increase by the same factor. If you double the voltage, the current will be doubled. If you triple the voltage, the current will be tripled, and so on. And of course, this is only when the resistance is set constant. Okay, now on the second part here, we are going to keep the voltage constant and we are going to alter the resistance. So let's say, for example, we'll start with a resistance of around 150 ohms. Okay, we'll keep the voltage constant, we'll keep it at 4.5 volts. And notice here when the resistance is around 150 ohms, the current is around 30 milliamps. Now what do you think will happen when we double the resistance? If we take it from 150 to 300, what do you think will happen to the current while keeping the voltage constant? Let's do the change and monitor what will happen to the current. So now I'm increasing the resistance. Notice that the current is decreasing. And now we are taking it to around 300 ohms. And you can see here, when we double the resistance from 150 to 300, the current decreased by 1/2. It went from around 30 milliamps to around 15 milliamps. That's 1/2. Now what will happen if we triple the resistance? Remember it was 150 ohms. Let's take it to 450 ohms and monitor the effect on the current. Okay, so now the resistance is at 450 ohms and the current was cut by 1/3. It went from 30 milliamps when the resistance was 150 ohms to 10 milliamps. Hence, resistance and current are inversely proportional when the voltage is set constant, meaning if you double the resistance, the current will decrease by 1/2. If you triple the resistance, the current will be decreased by 1/3, and so on. And the same thing, if we decrease the resistance by 1/2, the current will be doubled. So this is basically support our equation I equal V over R. The electric current is equal voltage over resistance. So from this equation we can write an equation for voltage in terms of current and resistance. So if I equal V over R, this means that the voltage is equal the electric current times the resistance, and also the resistance R will be equal to V over I, the voltage over the electric current. Now recall here that the unit of voltage is volts, unit of current is amps or ampere, and the unit of resistance is ohms.